Welcome to the tutorial on regression and classification. So in this tutorial, we'll use scikit-learn to solve a regression and classification problem on a materials dataset. So let us get started with the notebook. The first step would be to import the data and analyze the data. So the tools that we use for this are NumPy and Pandas. So let's start with importing NumPy as NP and Pandas as PD. And then let's load our dataset using Pandas. So let's assign a variable data to our dataset and use pandas dot read CSV. To import this CSV file named mechanical props kaggle process.csv. So this is a dataset obtained from Kaggle, which is an open source database, and this will be available as part of the course material to you. And let us look at the first few lines of data. So this is how our data set looks like. There are a few columns named ID, SU, SY, A5, etc. And here is a short description of what these columns mean. So if we click here, we see ID means a unique identification code for a material. So basically different materials will have different IDs. SU is the ultimate tensile strength in MPa. SY is the yield strength in MPa. A5 is elongation at break or strain as percentage. E is elastic modulus in MPa. G is shear modulus in MPa. Mu is Poisson's ratio. Rho is density. And the column U's determines whether the given material can be used as an EV chassis. So basically this is a data that contains the ID of different materials, various mechanical properties, and a column which states whether this material can be used as the chassis of an electrical vehicle. So the first step is to find out all the information that about the dataset. To do that, we can use the .info method for data frames. And here's what we find. There are 1552 entries. That means there are 1552 data points. And the different features are ID, SU, SY, A5, EG, mu, rho, etc. Most of them have 1552 non-null values. That means there are no missing data except for this column A5, which has 1346 non-null values, meaning the other values are missing. And the type of data, clearly ID is an object, so ID is not a number, so it's a string. And all other features are integers except for the final one, use, which is again a string that contains yes or no. So a machine learning model works only with numbers. So we need to convert these yes no strings into booleans or numbers 1 0 or true and false. Before doing that, let's quickly find out the total number of null values. We can do that by subtracting 1346 from 1552. Otherwise we can also use this is null method. So let me demonstrate how to do that. So data.is null gives a mask that has true and false value. A false value means the data is not null, and if the value is true for a cell, that means the value is null. So how can we find out the total number of null values? We can just use the sum method, which treats true as 1 and false as 0. So if we do that, column wise we get how many null values are there, and we see for all features except A5 there are no null values, and A5 has 206 null values. And the next thing is to convert our labels, that is use, yes or no, into numbers or booleans. One way to do that is to use the apply method that we discussed in the previous tutorial. There's another elegant way to do it. So let me demonstrate the other way, but you can always use the apply method. So the other way is using pd.getDummies function. So this basically takes in all non-numerical features and converts them into one hot encoded vectors. To do that, let me demonstrate you what happens if I pass data here. If I run this, You see these columns are all numbers, so that is not affected, but the IDs, so there are multiple different IDs, every ID becomes a feature, and every data point that has that ID has a value of true, all others have false. Clearly the ID is not very important here in classifying them as can be used as chassis or not, but the final columns, if we scroll all the way to the right, we see there are two columns, use no and use yes. So every material is either used as a chassis or not used as a chassis. So if it is used as a chassis, use yes becomes true and use no becomes false. If it is not used, use no becomes true like this and use yes becomes false. So clearly we need not use both these columns. The data in one of the column is sufficient to comment whether the material has been used as a EV chassis or not. So to clean this up, the first thing we need to do is get rid of these IDs. So let us do that below. We can set the ID as index maybe. So let's use set index, and if I press shift tab, set index takes keys and an in place argument. So let's let the keys be ID and let us mark in place equal to true. That means whatever changes are made, it is made in the actual data variable, and let's print data out. Okay, so ID I think is in caps. Yes, so we need to provide the actual name of the column, it is ID, and if we run this, we see the IDs have been set as indices now, and the next step is to convert this use column into one-hot encoded vectors. So to do that, let's use the pd.getDummies, and let's pass data here, and let's mark another argument which is drop first. So if we mark drop first as true, so one of the columns of use yes or use no will be removed. So let's see how this looks, and let's assign the data frame that is returned into data itself and print data again. So we see only use yes remains because we have set drop first equal to true, and use yes is sufficient to know whether this material has been used as an EV chassis or not. And finally we can see the correlations between different features. So let's use the core method to get the correlations. This basically contains all the features including use yes on the as the column names and the index names, and each cell represents the correlation between the corresponding row and column. So for example, if we look at use yes, it has a correlation of -0.1 with SU, -0.14 with SY, and we see that A5, which has a lot of missing values, has a very small correlation along with G. That means when we predict use yes using these features, probably A5 will not play a major role in the predictions. However, in this exercise, we'll first try to fill in the missing values of A5 using a regression just for demonstration, and then use these filled values to predict whether a material can be, to make a model that can predict whether a material can be used as an EV chassis or not. So this is just for demonstration. So let us get started with the regression problem. That means for all the missing values of A5, we want to create a model that can learn from the non-missing values and the other features and fill in the missing values based on what it has learned. The first step is to split our dataset into train and test. All the rows that have filled values of A5 will be used for training. The trained model will be used to predict the missing values of A5. So let us split our data into train and test based on the missing values of A5, and let's say data train is data dot, instead we'll use the drop NA function which takes in a subset argument, and our subset is A5. And then we need to provide an axis which says whether we want to drop the rows or columns. So since we are taking the subset as a column, we have to drop rows here. So axis has to be provided 0. And data test will be, so let's see how data train looks like. We see in data train all the A5 values are filled. To confirm that, we can also use the .info method. So here there are 1, 3, 4, 6 entries, and even for A5 there are 1, 3, 4, 6 non-null values. And to get the data test, we use data dot so let's obtain the A5 series and apply the isNull function. Let's see what this gives. So this basically gives a mask of true or false, and wherever it is true, meaning the A5 data points are not present, we want to get that for the test values. So let us pass this entire mask to data, and what we get in return is all the rows that have missing values of A5, and let us assign this data frame to data test. And let's quickly see the info of data test. We see there are 206 entries, and A5 has 0 non-null values, meaning all A5 data points are missing. So we'll train a model based on the A5 values that are there and try to predict all the missing A5 values. And the next thing is to get the features which we want to use to train the model. So our data train contains multiple features. Let's see what the features are. So these are the column names. And we want to use the available mechanical properties other than A5 to predict the missing A5 values. So these are our training X train. So we from this data train we want to remove two columns, A5 which we want to predict, and use yes. We do not want to use this variable to predict whether A5, to predict the missing values of A5. So this basically drops the columns A5 and use yes and returns a data frame which is stored as X train. We do the same for X test, where we, instead of using data train, we use data test, and again we remove these two columns A5 and use yes. And we drop the axes equal to 1, that means we are dropping entire columns here. And our Y train is basically just the A5 column of our training data. So let's run this and quickly look at all the X train, X test and Y train that we have obtained. So X train is our feature, contains 6 features. Similarly, X test should also contain the same 6 features, and Y train contains only the A5 values. Now let's go into applying our regression models, and we'll start with linear regression. And before doing that, some regression or classification models need that the features are scaled. Not all models need that, but a few work well when the features are scaled, and one of them is linear regression. So before training the model, let's scale all the features that we have. So to do that, we import this min-max scaler class from sklearn.preprocessing, and then we create an instance of this min-max scaler class, and we call this instance feature normalizer scaler. So let's run this. And the way we normalize our features is call this instance feature norm scaler, then use the .fit method. This basically learns the data from the given data. So that it learns the minimum, maximum, etc. from the given data. And we pass xtrain here. And we run this. So now this instance has learned the statistics of xtrain. Now we need to transform xtrain such that all the features are normalized. For that, we again call this instance after it has been fit, and then use the dot transform method, and then again pass our features that we want to transform based on the learned statistics. And let us return this to a variable named xtrain normalized, say, and then let's print xtrain normalized. We see this feature norm scaler actually gives out a numpy array. A prettier way to look at it would be convert this numpy array into a pandas data frame. So let us do that. So let us pass this into pd.data frame, and let's name the columns as they were. So let's say columns equal to xtrain.columns. So the columns name will be same as the ones that we have used, and the order won't be changed when we pass it through feature norm scaler. So once we do this, and let's reassign it to xtrain normalized, and then print xtrain normalized. So we get all the features here, and let's see the difference between the statistics of xtrain and xtrain norm. So we can use the dot describe method for that. So let's first look at xtrain. So xtrain dot describe. So this shows various features: their mean, their standard deviation, the minimum values they have, the maximum values they have, etc. And now let's look at the normalized features. So that is xtrain norm. And we see across all the features, so we need to use the describe method. And here we see across all the features, the minimum is always 0 and the maximum is always 1. So across the feature, the distribution has been changed such that the minimum value is 0 and maximum value is 1. So this is basically normalization. Now we also need to normalize our training features. But here we should note that we should not learn from the statistics of our test features, and we should only use the statistics of our train features to normalize our test features. So basically we need not use the fit function again, but just use the transform function. So let's again call this feature norm scaler and use the dot transform method and pass in the x test data. Again, it always returns a numpy array. So let's convert this into a data frame, pd.data frame, and the columns are the same as the column names in the xtest. So let's assign columns equal to xtest.columns, and let's name this instance as xtest normalized. And again, let's print out xtest normalized dot describe. So we see again more or less every feature lies between 0 and 1, but since the test statistics can be slightly different than the train statistics, that's why the minimum is close to 0, not exactly 0 for all features, and the maximum is also close to 1, but not exactly 1 for all features. Now that our features are ready, we can perform the linear regression. So for that, the steps are common throughout different regression models. I'll demonstrate how to do that for two regression models, that is linear regression and decision trees. So the first step is always to import the model. So we use from sklearn.linear model import linear regression. So linear regression is a class inside the sklearn.linear model module. And after we have imported, we create an instance of our regressor class. So let us call this instance LR model, so linear regression model. and we create an instance of linear regression, and then we train the model. So just like our scalar function, we have the fit function here. So we just have to call our instance and then dot fit. This means basically the model is learning from our training data. So we have to pass both all the features and all the target values. So our features are X train normalized and our target values are Y train. So once we learn this fit function, the model basically learns how to map your X train normalized into Y train. And once we run this, our model is ready, our model is fit. And if we click on these parameters, we see there are a few hyperparameters here. You'll learn more about what hyperparameters are in the following lectures. And for example, the hyperparameters are fit intercept is true. That means the linear regression will have an intercept. There are other hyperparameters like copy X, tolerance, number of jobs, positive, etc. You can get more information about what these hyperparameters mean by placing your cursor here and pressing Shift tab. And basically you can set what these hyperparameters are. By default, fit intercept is true, copy X is true, tolerance is -10 to the power -6, etc. And you can find out what these means. For example, fit intercept means whether to calculate the intercept for this model and so on. You can go through this on your own. So once our model is fit, we can use this model to predict our missing values. So to do that, we can use LR model dot predict, and it has to use all the features of the test, all the test features to predict the missing values. So we pass X test normalized, and if we run this, we see these are the predictions of the missing Y values. So let us assign this to a variable, say Y linear regression predict. And we want to visualize how the predictions are for the train set. So let's create another variable called linear regression predict train, and let's try to predict the training data itself. So let's pass X train norm itself, and let's visualize how good the model is by creating a plot of the actual training values on the x-axis and the predicted values on the y-axis. So to create a plot, we can use the matplotlib function from pyplot. So let's do that from matplotlib dot. So we want to import this function as PLT, and plotting is very simple. Once you have imported this function, you just have to type PLT dot scatter. So scatter basically creates a scatter plot, and PLT dot plot creates a line plot. So we want, after this PLT dot scatter, we have to provide the x values and the y values. So let's say our x values are Y train on the x-axis and Y linear regression predict train on the y-axis. And just to get the parity line for this prediction, let's just plot these two on the x and y axis both, so that we have an x is equal to y line. And then we can add the labels for x and y axis. So let's say the x label is true values, true train values, and the y label is predicted train values. And then finally we just have to call this function plt.show. This will basically create a plot. So this is how our data looks like. Basically, this, had our linear regression model be perfect, then all these data points would have lied on this line x is equal to y, but our linear regression model is not perfect, so there is quite a lot of deviation from this y is equal to x line, which is called the parity line. And this is only the visual representation. We can also get a metric, a number for how good our training has been. So to do that, we can call the mean squared error and the mean absolute error functions from sklearn.metrics. So let us import this and then pass our predicted and true values to these functions. So mean squared error takes the true values, so that is y train, and the y linear regression predict train, and it computes the mean squared error, and we want the root mean squared error so that our error is in the units of the feature that we are predicting. So let's take a square root of this using np.sqrt, and let's store this as root mean squared error. And let's do the same for obtaining the absolute mean square error. So mean absolute error. So let's call this MAE, and we need not take the square root because mean absolute errors are in the same units as the training as the label target feature. And let's use this function here. And let's print out the MAE and the RMSE. So let's say RMSE equal to RMSE error and print MAE equal to MAE error. So we see our training errors are 8.7 for RMSE and 6.6 for MAE. Now let's use another regression model and compare how well it performs as compared to linear regression. So for this we'll use the decision tree regressor. The coding process is almost the same, except that decision tree regressor will is imported from sklearn.tree, and then we create an instance of this decision tree regressor, and then we fit the model. So our x train variable is basically x train norm and y is y train. We run this. So our decision tree is ready. Here also there are some hyperparameters like criterion, splitter, max depth, etc. You learn about this hyperparameter later on. This is just a demonstration. Now again let's visualize the predicted and true values. So let me copy the code above. So this is for visualization. Let me copy this and paste it here. The only difference is we are using the decision tree model instead of the linear regression model for prediction. So let's use DTR model.predict, and everything else let's change LR to DTR. Here also LR to DTR. We need not import this again because Python already knows that this function has been imported. Again DTR, DTR. And let's run this. Maybe let's change the colors of the scatter and the line plot. So let's say color equal to orange. Let's rerun this. So we see visually the predictions of the decision tree model look much better. And let's also again compute the root mean squared error and the absolute mean error. Mean absolute error for decision tree regression. So the code is already written here. This is y train y DTR predict train. So this is we have to first pass the true values. So that is y train, and here y DTR predict train. And similarly for the MAEs. And once we run this, we see the RMSE and MAE are much lower for the decision tree model than for the linear regression model. So basically this model performs better in predicting the A5 values. Now let's use the better model, that is the decision tree model, to fill in our missing values of A5. For that, we need to predict the missing values of A5 using our test features. So let's say y test predict is DTR model dot predict, and it will use the X-test normalized feature. Because it has been trained on normalized feature, we have to provide the normalized feature for testing as well. And let's see how y test pred looks like. So these are basically the predicted values by our better model, this is decision tree model, for all the missing values of A5. The next thing is to fill in the missing values of A5 in the data frame. So our data test contains the missing values of A5. So let's call the series A5 and assign it the predicted values, that is y test pred. And then let's print data test. So there's a warning, but it's okay, we can use this method as well. Now we see all the A5 values have been filled in, say 6, 6, 6, etc., 12, 7, and this is what we have predicted as well. So first few are 6, 10, 5, 22, etc. So now we have filled in all our A5 values. The next thing is to combine the filled and the training data into a single data frame, and then train another classification model which can predict whether a material can be used as a EV chassis or not. So to combine two data frames, we have to use this pd.concat method, and within a list we have to provide both the data frames that we want to concatenate. So our data frames are basically data train, so data train and data test, and we want to concatenate them along the rows. So that's why we have set axis equal to 0, and we have said ignore index equal to true. That means our concatenated data frame will be indexed from 0 to 1. We can set it to false as well, so that we can map an index to its ID. So let's set this to false and store this data as filled data and print this out. Here we see the IDs are maintained and all the A5 values should be filled. So to quickly confirm that, let's use this filled df.info. Okay, the variable name is filled data. So let's replace this here and run this. Now we see all rows or all columns including A5 have 1552 non-null values, and our use yes is a boolean. So our data is ready for performing a classification task. Now let's go ahead and train a model which will learn from all these mechanical features and predict whether this material can be used as an EV chassis or not. Now for that, let us use a separate train and test sets, and there is a nice way to split our data into train and test set using this train test split that is present in sklearn.model_selection. So let's use this train test split function. Let me run this first so that I can access what are the arguments required for train test split. So let me call train test split and press shift plus tab. Basically I have to provide the arrays, the test size or the train size, any one of them is sufficient. Shuffle is by default true, stratify is none, and we can provide a random state to ensure reproducibility. So let's provide filled data here. Let the test size be 0.2, that is 20% of our entire data, and let us set a random state of 1, and the return, it will return two arrays, that is the data train and data test. Let's run this and look at data train and test. So data train dot info, it has 1241 entries, and data test has about 311 entries. Now we have to separate the training features and the labels, so as done previously. So let's use xtrain for training features, and we say data train dot drop. We just want to drop the use yes column because all other columns are our features. And similarly for xtest, we just use the data test. So let me replace this with test, and then we want the y values. So y train is data train use yes. So I'll pass uses within a list so that we get a data frame as y train. So y train will be a data frame. Similarly, y test. Let's run this and see. Okay. So for drop, we have to provide the exact keyword. So the labels is use yes, and we want to drop the entire column. So we have to provide x is equal to 1 because we want to drop the column, and same for this. Let's provide the labels keyword as well. We have 2 commas. Yep. Now this is done. Now let's look at xtrain, xtest, ytrain and ytest. So xtrain are all the training features, 1 to 4 1 rows, using which we want to predict use, and ytrain are all the use yes values. Similarly, xtest contains all the features, and ytest contains all the use yes values in the test split. Now let's again create a decision tree classifier model. You will learn later what this means, but let's see how to implement this code. So from sklearn.tree, we import the decision tree classifier model. As usual, we create an instance of this model. So DTC model. This is decision tree classifier. Let me copy paste this. And then we train the model. So for decision tree based models, we need not normalize the features. So we are not normalizing our features again. We'll use the usual features. So we use DTC model dot fit, and we pass the x train and the y train values. So this row basically gives all the features that we have used to predict our use yes values. And finally, this is a classification model. So one way to visualize how good our classification has been, both for the training and test set, we can use a confusion matrix. And the way to build a confusion matrix is import the confusion matrix function from sklearn.matrix and a confusion matrix display function that will plot our confusion matrix. So basically, we will predict our y train values using DTC model.predict x train, and then we pass the predicted values and the true values to this confusion matrix function and store it as confusion matrix. And then we pass this confusion matrix that we have stored into this display function, into this display class confusion matrix display, and store it as another instance called confusion mat plot. And then we use the dot plot method to plot the confusion matrix. So this is basically our confusion matrix for our training data set. We see there are no wrong predictions. This is usually a red flag, and we'll learn more why this is a red flag. But for now, let's see how this model performs on the test set. So on the train set, it is perfect. So it predicts all zeros as zeros and all ones as 1. It does not predict any 1 as 0 or any 0 as 1. So these diagonal boxes are zeros here. Let's do the same for our test set. So we use the same code as before, just that we use our test features here. So these are data points that our model has not seen and predicting without seeing these data points. So we do the same here, And we see that even for our test set, the model performs pretty good, but it gets one data point wrong. So basically it predicts one value or one true value as false here. Otherwise this is doing pretty well. And these decision tree models can also give you a feature importances, meaning which feature are more important in predicting our target values. So if we use this feature importances method here, or a feature importances instance here, we see a few features and the numbers. The higher the number, the more important it is. And to see which features these actually map to, we can use this feature names in method. This gives the feature names in order of the feature importance vector. For example, SU has a feature importance of 0.52, which is pretty large. But if we see the 0, first, second feature A5, which we have predicted using linear regression, it says the feature importance is 0, which means even if we removed this feature, probably the prediction would not have changed much. But the regression problem was just a demonstration of how to use sklearn to perform a regression task. And finally, we'll look at a brief summary of the syntax of sklearn. So for every machine learning model, we usually create a train test split. The way to do that is import the train test split function from model selection and pass your entire data. It gives out a train data set and a test data set. You can tune what size of train and test data you want using this test size or train size variable. Again, to train any model, the syntax is also very simple. You need to just use sklearn.some module name based on what model you want to use. For example, for decision trees, the module name is tree. For linear regression, the module name is linear models, etc. Once you import this model, you create an instance of this model and call this fit function and pass your training features and training labels to fit your model. This works for both classification and regression tasks. And finally, you can predict what the model has learned using the model.predict, and this works only after you have fit the model, basically only after your model has learned the data well. And after that, you can use any metric from sklearn.metrics to find out how well your prediction has been. So this is all from this tutorial, and I'll see you in the next tutorial.